But then I realized that I don't know what CFT is, and this is why I'm doing math. So I started to study physics. String theory and CFT was somehow something very amazing and fascinating to me, but I couldn't figure it out. So yeah, so maybe one question for the whole program for me is, what is CFT even? And before I can present any tools, I should somehow understand that. So maybe the topics should really say is some kind of point of view from probability to understand CFT. So let's say here is point of view instead. Okay. And yeah, I forgot to say that please interrupt me and ask anything if you want. So I can go to various directions because my notes are kind of sketchy anyway. So I would like to be more interactive than just giving you precise things. I'm trying to write notes. Let's see how it's gonna go. So I don't have notes yet. Okay, and then, I don't know, so you can Google CFT, you get a lot of things. Maybe from the probabilistic kind of idea, there are various points of view that you can take. One that's good for simple-minded people like me is somehow discrete models. So models are lattice. And here, of course, you want not arbitrary ones. Maybe, let's say this is all in 2D, okay? Because I'm a simple mathematician and I don't know how to do high dimension. So then here also 2D. And maybe you learned in some class that statistical physics models in any dimension, when you take some kind of scaling limit, it should become a quantum field theory. So QFT, right? And well, again, I don't know what QFT is really, but CFT is something that has conformal symmetry. Is in addition. And what I need to have here is critical. Also, let me know if you cannot read. I tend to write kind of small. Okay, so that's one point of view. So you try to discretize and understand your theory in that way. So here is some kind of scaling limit. It's gonna become a little bit more precise later. But first I wanted to, because maybe we can invoke some discussion here about what CFT is, because we're gonna have different people here, as far as I understand, giving different types of points of view. So another probabilistic one is the path integral. I just mentioned it here. Because we will have lectures, I think, next week about it. So there should be some kind of, I don't know, action functional, and you integrate over some big space of fields. And you describe your theory this way. I think Remy will talk about this. Probably. So I will not really talk about that much. Right. So then there are various other points of view which may be more geometric or algebraic. So you could say because of the conformal symmetry, we have the symmetry algebra, which is the Virasoro algebra. So you could just say that you study representation theory of the Virasoro algebra. Actually, when I was a student and I was asking people what is CFT, some people told me, yeah, it's just representation theory of Virasoro algebra. So you might oppose because there are higher symmetry algebras, etc. So maybe plus. And there's all geometry underlying in our space-time. So maybe this is also, I guess you can actually put it here as well. But people who do representation theory, you could just ignore all that and try to study this. So this is maybe more in the kind of Hilbert space of this theory. So I'm putting a lot of words here. If you don't know some, it's okay. I'm just trying to put pointers to different people because they may have different kind of name list in their minds. So, okay, that's something that came to my mind. And maybe from here, I think we're gonna have a VOA course. So you could formulate if you want to put the geometry there. So there's maybe this is a bit more, I think they're kind of connected, but again, I'm not an expert in this. So I should maybe cross, this might appear a little bit in my talks, this for sure not. But this will be, I think, Thomas. Okay. So then there's the geometric point of view. So you could say, what is your theory? Where is it living on? And I already said 2D, but it could be some surface. So you could say, on Riemann surfaces, which means there's some complex structure, or you could do topological, but then again, you ignore something. So this is maybe more like a la Segal, maybe Kontsevich, etc. By the way, I am not going to be able to cite correct people in correct places. Apologies. I'm not even intending to remember who did what. So you might point out or ask if you think it's relevant that I'm ignoring some contribution, for example. So I'm trying to convey the ideas. Yeah.
Thomas will give lectures.
Yes, that's what I meant by talks.
Sorry.
We can say lectures, yeah. There's a bunch of lectures, but I noticed that these ones are maybe explaining a little bit what CFT is from those points of view that I cannot. Yeah, so the geometric one, there's some kind of functorial description. So you kind of have a, functor on surfaces or cobordisms, as they say. And it goes to vector spaces or maybe some modules. And they might feature in some, I don't know what they're gonna do these other lecturers. So maybe this will feature in some talks. So I will not gonna be able to really talk about this either. I think we will see something toward this direction. Okay. So this is when I was thinking last night, what is CFT? I don't know if I forgot some. Maybe there's one more that you might kind of add, and maybe you guys have more. So luckily I have a little bit of space here, because then, so what, yeah, it's impossible for me to give probabilistic tools to all of these things, right? So I need to start from something that I understand. And what is physically useful is correlation functions. So you could say that because you expect that the theory has some fields, which are the physical observables. So be it random variables in these probabilistic models, be it some primary fields that generate a Virasoro module or some higher W algebra module, whatever. Be it an insertion on a surface with some structure. You want to understand how those observables, what they describe and how they interact, right? And this makes sense to me. So maybe the theory itself, like what does it mean? The definition is not clear. But what I can observe, I hope is also for physicists kind of makes sense. You observe something and you see how things are correlated. So then, of course, here, you need to have some kind of consistency conditions, right? And maybe, yeah, some symmetry properties. Maybe something else. So you could say that if you have some kind of consistent collection of these things, that is your CFT, for example. And then it describes certain observables that you've chosen to study. And maybe there are more that are not included in your theory, but that's okay, right? So somehow, maybe the idea here, so here, of course, would be conformal invariance. Here, I don't know, like I'd like to say crossing symmetry, etc. I think there are experts here who maybe can list more than me. So we will see something from a concrete description soon, okay? So somehow the idea that I decided made sense was that if you have somehow find or say, yeah, find kind of consistent system or rather maybe collection of endpoint functions, let's say. N is the number of insertions, so n natural number, whatever. Describing desired observables, let's say. Okay, so what does that mean, right? So how many of here does not know what's the Ising model? So raise your hand if you don't know what it is. One person? I can describe you on the next board a little bit. But I just want to point out here that's an example, a very simple one. Before I go to the board, so you could say critical Ising model CFT. It's supposed to model some magnetic material, and it's supposed to have somehow magnetic spin up or down. So there's some spin observable, which is usually denoted sigma, or at least I'm used to it. Then there's something that describes energy, which maybe often is called E epsilon. And it's somehow maybe between two nearby spins. What is the energy cost of them to be opposite or the same, something like that. And okay, there's some identity field just for the consistency. And then there are some rules how they interact. And this, if you look at correlation functions of these kind of three things all together, you see this such a consistent system. And it's motivated from some actual model. But actually already from the CFT, so this model is discrete. So I'm mixing the discrete and continuous here. So I'm somehow saying already like CFT for the discrete model, which means I've taken some limit. But then I don't know exactly how to describe the limit rigorously. So I imagine there are these fields also in the continuum model. I don't know how to make sense of them mathematically, but I know how to make sense of their correlation functions. So that's somehow one option of Ising model CFT. And this has a very probabilistic point of view because the model can be defined probabilistically. Okay, so I'm gonna draw you a picture about it, and hopefully that helps for who doesn't know the Ising model. So So 2D, as always. Maybe let's say it's on some Z2 grid. So, and finite volume, because, so let's say, we cannot draw infinite volume here anyway. So let's say we have some box. And the grid, right? Something like that. And the model, it has the spins, like at each vertex, say sigma x, which I can say is plus or minus 1, which is up or down. So x is in the grid. D is some domain, like the box, say. And I'm imagining R2 is complex plane because I want the complex structure. Okay, so there are two types of spins, and maybe I don't care about the other things too much because for my purposes it's not important. But I could say, yeah, up or down. So there are two colors. And here I could have used a nice presentation with simulations, but maybe this will do. So I assign them here randomly according to some Gibbs measure that I should maybe tell you what it is. Or you can Google it or ask ChatGPT. I don't know if it will give you the correct answer. Okay. So I don't know if this looks like the critical one because I'm doing it very, randomly. But each configuration will have this collection of spins. And when I'm in the discrete, of course, everything is good. I have finitely many spins. So I can say there's some discrete spin field, right? And then I can ask, okay, so how are some spins correlated? So maybe here is some sigma x, and here is some sigma y. So I pick some vertices. Let's say this vertex set is V because I'm a bit lazy to write all the time. So then I can say correlation of these guys is kind of their interaction. And I guess properly I should write it. So there's a probability measure, the Gibbs measure, which I didn't write to you. But there's a measure which gives weight for each configuration, right? So then I can take maybe the product and ask how they are correlated. Or maybe I should subtract the mean. So depending what you want to call a correlation. Maybe a physicist could tell me which one is more proper.
Yeah, we take out the average.
Yeah, I was kind of wanting to do that. So let's do that. Average might be sometimes 0 and then it doesn't matter. So then it should be like the product of them. Like, okay, so this is if they were completely independent. Somehow the averages are just the product of the average of the pair is the product of the guys. But maybe it's not quite true. So then you look at the product of the pair and average, right? So yeah, this is somehow in the measure. Okay, I guess we call it. I hope you are kind of familiar with this notation. So I forgot the Gibbs here. So this is the expected value with respect to that measure. I remembered that I actually never studied probability in my life, and now I'm teaching it. It's funny. And when I started to learn these SLE curves that I want to tell you about, I didn't know what this symbol meant because the first year probability class that was mandatory I already forgot. But measure theory I knew, so somehow it's just a measure. It's a probability measure, so it's normalized to have mass 1. So please ask if I write some symbol that you don't know what it means, because it's maybe not so complicated. Yeah, so maybe I should say what the measure will look like, just to, if I remember, let's see. So I have this configuration. The spins in all vertices. So I assign some probability to each configuration, and it's going to be up to normalization. So let's say proportional to, let's see, exponential. And I do the nearest neighbor model. So then I'm just looking at these kind of products. Let's write like that. So this means there's an edge in this graph. Okay. So only the nearest neighbors interact directly. And then I want to have beta. So beta is positive, maybe. It's the inverse temperature. And because I want ferromagnetic, maybe I want 2 minus signs, so there's no minus sign. Okay, so formulas might be a bit wrong because I actually didn't prepare the formulas. But the idea is this is some kind of Gibbs measure. So you can just think about the model as modeling this kind of configurations with some kind of nearest neighbor interaction that you encode in probability weight. And then you normalize so that the total probability is 1. So I hope it somehow makes some sense. And we don't always have CFT because I said that there has to be this criticality. So there should be a continuous phase transition. So maybe some kind of note here. So we get CFT only at the critical temperature, which is somehow T critical, which is for 1 over beta critical. Okay, maybe also in infinite temperature, but let's not discuss that. Okay, so this is somehow, you can study properties of this model and see that this is the fixed point of the renormalization group flow if you want, or that this is the only kind of scale invariant. Model. So this course is not about statistical physics, so I'm not going to go too much more in this. But I hope it makes sense that if you change this inverse temperature, then you're going to change how much these spins want to be the same next to each other or different. So if you penalize very much that they are different, so then many of them want to be the same. So this is the low temperature phase. So there the sign here would be important. So you can tell me if the sign is wrong and I'll fix it. And in high temperature, they don't care too much. And then every configuration is kind of equally likely. And the system is very disordered. And somewhere in the middle, there is some kind of critical point, which is, yeah, so this is some non-trivial number. I guess for the square lattice, I forget, it has some square root 2's in it.
So maybe there is a minus sign here.
I was thinking because, yeah. So if we want, let's see. We want low temperature is penalizing different. No, so if they are different, then this product is -1, right? Because 1 is plus and 1 is minus. So then actually, I think it shouldn't be.
If our ferromagnetic is favorized, no?
Yeah, so I want the ferromagnetic one. So the
yeah, you are right. Yeah. It's not.
I thought it's maybe. Anyway, you can. it's an exercise to figure out if my model is correct. But does the idea make sense? So,
Eveliina,
yeah.
I'm just, for me, I'm in the conformal little box, the conformal field theory box. So for me, the Ising model would be like the Virasoro at central charge 1/2, and I would have these two modules. Can you help me understand if I go outside my box, what happened with that little?
yeah, so I think you are talking about kind of the orange, but not in the correlation function point of view, but in the Virasoro.
Yeah, I mean, I can make the correlation functions, but I am just with my Virasoro VOA at central charge 1/2, and I have, what, two other modules?
Two other, what?
Modules with
Modules.
1/16, and what is it?
Yeah. Let's see. So it should be, central charge 1/2 CFT with primaries. So these primaries give the modules. So there's the sigma energy, which is the product of two. So I guess the energy appears in here.
So normally my energy.
So this would be energy at the x, y edge. Okay, and then identity. And let's see, this one, I think it has the 1/16. This has the 1. How does it go?
1/4, I think it is, yeah.
Okay. 0. So what is this? Is the L0 eigenvalue?
1/2.
I wanted to say 1/2 and 1/8, but
I think it's.
okay. So I can.
No, it's 1/4 or 1/8. The VOA itself is central charge 1/2, and that's where your L0. Giving your eigenvalues.
Let's see. So the correlation function. Maybe I can write like that. So this is abused now. But if it was a continuum field, like at x and y, I identify the point and the deviation. Sorry. Let's say just x minus y. So you're interested in that power, right? And I think it's 1/8, maybe negative. Here is x minus y minus 1/2. And okay, here is modulo my minus signs, factors of pi and factors of 2 are always wrong in my lectures.
Right.
That's why I try to make you notes so that you will actually get the proper. Okay, so yeah, it should be this minimal model. People call it minimal model. And there should be a Virasoro action. What should I call them? So somehow, yeah. On, how should I call them? So there's a module for the sigma and a module for the epsilon. And I don't know how to, because I'm a little bit less in your area. So I'm having trouble kind of telling you the thing. But this should be a highest weight representation of this weight. Maybe
1/16.
Yeah.
This is for chiral, no? We are talking about chiral.
So now, yes, so I'm mixing chiral and antichiral.
Well, you would have left movies and right movies, it would still be 1/16.
Let's say just it's h of sigma, and I'm not quite sure what it is.
I think the 1/2.
H is usually the,
Yeah, but
so the correlation function is here. So it's just the 2-point function. And then this has the h. And this is just the trivial.
And since you brought it up, we are just dealing with chiral.
Right. So where I will go to next is actually fields on the boundary, which is kind of effectively chiral. So I have my box, so I could study field, I don't know, there, whatever. It's like boundary field in some sense. So I want to make a clearer picture about it soon. But this would be kind of chiral. So in the bulk, of course, you have the full. So you have chiral and antichiral, and then I should be a bit more careful what this modulus means, because it should be a tensor product of chiral and antichiral. So this is somehow up to correcting it, let's say. So this would be the full. Some people call it full, which means, yeah. So maybe the chiral part is here, and the antichiral part is just another copy. And then, yeah, then you need to tell me how do you want this to be written, right? Does it help?
Yes, but so my question is, this is just some limiting point in your picture.
Right, exactly.
So is there a way for me to understand how this is being deformed or being moved off of this critical picture that I'm comfortable with? Once
from the discrete, okay, so not really, or I think there might be some other expert who can explain better. So you can look at the perturb where you're not at the critical point, but a little bit nearby and see what happens. And you get some massive theory, something like that. And then you can try to see how they, yeah. But for me, I just want to fix the critical point where I know that it converges to the scale invariant theory. And I don't care about the other temperatures, right? And then, so what people can prove is that if you look at these interactions, they do converge to correlation functions, which are the same as what you get from this. So in that sense, you can say they are the same. And actually, people have also constructed a Virasoro action corresponding to these modules at the lattice level. So this is quite cool. I think I cannot explain you. Kalle Kytölä did that. He's coming here next week, and I don't know, he might even talk about it. Maybe you ask him. Okay. So you see the Virasoro structure very well for the Ising model and for the so-called Gaussian free field, but not for all lattice models. Somehow it's not clear. But this is a nice example because you start seeing how different things interplay. Yeah, and then you really see that you get these primaries with the correct dimension, which I probably wrote wrong, but anyway. Let me switch them. Maybe you can see to erase. So while I erase, if you have any more questions, please. So yeah, somehow because these other things that I'm just erasing are a little bit too complicated for me, I thought the correlation functions are kind of simple because I can just write it and see what happens. But I don't really want to talk about this discrete model too much because there's something more interesting that I think is worthwhile. And because I'm expecting maybe Kalle will talk about those kind of things in his talk I think next week. So want to point out something. So this thing here, yeah, I wrote minimal model. There are only these 3 fields. And you look at their correlation functions, great. And you should take maybe the ones in the bulk, have this full chiral and antichiral. And ones in the boundary are kind of chiral, whatever. But the thing is that in this model, there are more observables. And I'm interested in something else, which is not here. By the way, I have no idea about the time. So you should somehow indicate whenever the Russian seminar style talk is going too long.
25 minutes.
Yeah, great. So, So maybe somehow, yeah, what is more? So that was a simple-minded example of a CFT that you can study, and actually quite a lot rigorously analyze. I should have mentioned many names there probably, like Smirnov, who got the Fields Medal understanding this model, and other models. But yeah, like I said, I'm not gonna list. I think it's too much to try to list all the amazing people who worked on this. But let me do the box again, but a little bit more curvy. So I want to be always in planar domains. Again, because it's the simplest. So let's say planar, meaning no metric, flat metric, simply connected. So what does it mean is that there are no holes. Or in a fancy way, I could say that there is a conform map to the unit disk. Let's see. Call it something. Depending on how you wanna look at things. So I want no holes just because mathematically it's harder if there are some holes, keep track of them. So there are generalizations you can do, but let's not worry about it now, okay? So then I could imagine I had my Ising model here on some grid or some other model, but maybe the Ising is the easiest to think about because I can put the two colors and try to see what happens. And of course it becomes a mess. So there's two colors, but it's impossible to say, you know, much about it, at least without doing some complicated stuff. So in simulations, you see how it looks like, but simulation is always discrete, right? There's tiny, tiny, tiny grid. So then in the limit, I'm not able to draw those colors anymore, but I can study how the correlations behave. I can study something else that's a little bit more geometric, which is what I want to do. So let's impose some boundary condition. So this is still finite volume, right? So there's boundary. Boundary condition. And of course you can take various ones. Maybe people say it's locally monochromatic. On segments. I will draw it. So monochromatic means that it's either, maybe plus should be red, plus or minus, right? So, and the segments are fixed. So I could say, now I'm gonna be interested in the boundary insertions, because what happens is that, let's say here is one point, and I'm declaring that the boundary is all pluses on this side, up to some place, minuses here. And well, because I'm in the plane, I need at least one more point somewhere, because otherwise I go around and there's a contradiction. So I could put maybe, say, one here. Something there. Let's do 4. Right? So these are boundary segments where I fix the system's state. So if you're interested in some other model, you can imagine similar kind of alternating type condition on the boundary. And this should be some kind of disorder insertion, right? So I don't know if you, maybe some of you are familiar with it. Cardy studied it a lot. He was calling them boundary condition changing operators. boundary condition. Or BCC, right? BC. And actually they have interesting correlation functions. So you might think about, yeah, it's quite boring that just already everything is fixed. Inside, I still do my Gibbs measure as before. And okay, so because the vertices spins on the boundary are fixed, so in the interaction that is there, the spin next to this boundary is interacting by the same way, but here is always plus, and here it can be plus or minus, right? So I can use the same definition. But now if you simulate it, of course, what you're gonna see is these two different colors, which I'm not attempting to draw. But what I can draw is some kind of frontier or interface because of planarity again. So if I'm somehow exploring, okay, so maybe there's some stupidity that here is plus and here is minus, like that, if it's a square grid. So let's maybe forget about this because it's a microscopic effect. So you need to make some decision then how to explore maybe everything on the rightmost. So in the limit, it's not gonna happen almost surely anyway. So let's say it was starting like this, just for simplicity. And then I can follow wherever there's a different spin on one side, right? And a different spin on the other side from each of these. So I get some interfaces and somehow they have to connect in some way by planarity again. And somehow this was a very interesting model for mathematicians to study. Not really from CFT point of view, because they kept telling me 10 years ago that CFT is nonsense. So sorry about bad jokes. I hope you will tolerate it. I mean well. So yeah, not only me didn't understand it, but now we had huge developments in the recent decade actually on the CFT side. But this started earlier. So somehow for the math community, maybe people call it random geometry now, or even some statistical physics, or probability theory, whatever. So I think it was 1999, around that time. So there was a guy called Trump. And he was interested in what these interfaces look like. Such interfaces, let's say. And the question was, so what is it in the scaling limit? So it becomes some kind of curve in the continuum. So it should make sense in the scaling limit. So scaling limit now means that I've got here my grid intersected with domain, but I scale by some delta. Epsilon was already used, that's why delta. So scaling limit means delta go to 0 so that the grid disappears. So, and there's a plethora of models of interest to probabilists that actually these questions became very prominent, not only the Ising. And now you could say that, where is the critical temperature? I could do it in any temperature, right? And yes, you can, but it becomes somehow different in different temperatures. And let's see, low temperature, they just become some kind of very straight, smooth things. So it's maybe less interesting. High temperature, infinite temperature, it should become like percolation, I guess, but it's harder to study. So the critical temperature is where these interfaces, which are the yellow guys, they are scale invariant somehow still. And that's when it's at the phase transition point. So that's where statistical physics people were interested in how the system behaves in particular. So that's why I'm also sticking to that case still. Right? So, okay, so you could now, if you're familiar with this Cardy's theory on the boundary CFT, maybe you already know what the disorder insertion is. And maybe you say, yeah, it's this whatever is dual to the spin. It's called mu sometimes. I don't know if I want to do this, but let me write it anyway in case someone kind of seen it in the physics course. So I want to introduce some disorders here. And if I go to this kind of Fortune-Castellan representation, if you know what it is, of the Ising model in terms of those contours. So there are other contours as well surrounding the components of the all plus, all minus. So there's some kind of duality, people say, where this disorder becomes kind of spin in that model. But maybe let me kind of cross it because I don't really. You can make sense of it in the discrete. But somehow the point is that it is some kind of predicted operator in the theory. But it does not really match any of those three things, which is why I want to try to convince you why that's the case. So then I'm going outside of this theory. Okay, so here should be some kind of curve in continuum, right? And scale invariant, and actually conformally invariant. And when you study those curves, what the correlation function is somehow the interaction, how they, what happens here, like how do they connect together? Something like that. So it becomes more geometric, maybe, and less maybe intuitive from this classical point of view. So then somehow maybe the problems here is the first one. It's already here. Somehow describe the interface in some useful way. Okay. So I could do, and I don't have my colors, plus minus, just one, and then there would be this interface. And there's no interaction if there's just 2 points. So that's the baby case. And then you could ask, how do several how they interact? And this is somehow correlations. Of this BCC operators, whatever. And then, okay, so what is somehow useful? Maybe then some implications. Let's see. So one nice thing, maybe theorem or something like that. I'm not gonna state anything, so just couldn't figure out, maybe it could be T1. Okay, so you can describe or solve crossing probabilities So people are interested in if there's many of these interfaces, in some condensed matter business. Let's say you actually have some material, like what kind of crossings there are of one state. Maybe in the percolation theory is more prominent. Like if you have vacant edges and, I don't know, free edges, like ones are holes and ones are kind of material, then you want to ask if there's a hole going through something like that. So this would be a probability of a crossing in the random model. Maybe another one is somehow describe the related CFT. So what does this now mean is that I decided my observables that I'm interested in are those interfaces. And then I decide that my CFT is whatever describes those observables, right? And this needs to be in some consistent manner. Yeah, and maybe there's further questions then. For example, find this Virasoro action, etc. And connect to these other things. So there are theorems and questions in this business. It's kind of maybe still ongoing area of research, but there was a lot of progress from, right? This is around 25 years ago, so Schramm had this paper. Quite soon after that, there was a rigorous description of what happens for one interface, which was here. So that's the first thing to start from. And then, when was it? 15 to 10 years ago, this kind of interaction had been, or kind of started to make more sense. In the math community, I mean. So what I wanted to say in these lectures is maybe how to understand this CFT related to those curves. And yeah, how it shows different features than just a minimal model from this probability perspective or point of view. And how you can, for instance, you can construct from here, you can construct correlation functions, which is this kind of description of the theory. So here should be the correlation point of view. And it matches with certain kind of Virasoro module structure. So then what is maybe remaining is how to describe, if you can construct actually a Hilbert space where the Virasoro acts, etc. So here is going to be no extended symmetries, so you can have more complicated things which have that. But maybe that's already would be too much for our description. Let's see if I forgot anything from this. So what I wanted to go to next is kind of telling you what these yellow guys are. And that's a little bit tedious because it has analysis and probability in it. And of course, I don't want to go to all the detail because it's going to be like a semester course. Let's see. Before that, so what is the answer here, maybe? So that's the first thing I need to tell you about. So these are called Schramm's SLE curves. So I need to tell you what they are, because I think not everyone knows. And okay, so these are then interacting SLE curves. And here, this correlation function perspective is what we get here. So it's somehow relatively explicit. which is nice for simple-minded people like me. So I'm a bit scared always of the BOA and even the geometric picture of CFT, because I don't know, it's harder to relate to something concrete for me. I need to erase again, but if you have any question, or you can make wishes what you need more explanation about. Yes, I didn't prepare yet the Wednesday and Thursday lecture very much, so I can adapt to your, what you think is the most helpful thing. Or if my perspective is too narrow, you can also complain and I'll try to make it more broader. But so the upshot of the philosophic discussion and the thinking I was doing about what CFT is, for me, is that there's different ways to understand CFT. It depends what you want. And here I want to describe certain observables, which I'm claiming you they are interesting. I hope you will agree. There are, of course, many others. One I just erased, which was the Ising model, minimal model, which is kind of already understood. So thought maybe that's not the best topic to describe. So the point of view is really understanding observables, and that's why we need to understand correlations. And in this particular model, first we need to understand the objects, which is these curves. So that's somehow the first step. So then I had this question, what is CFT? So now, what is this other acronym about? So it stands for Schramm-Loeffler evolution, or yeah. Sometimes this is stochastic. That he was calling it. Why evolution? Because if you look at the picture there, you can kind of dynamically describe where the interface goes by just following it, right? Step by step. So it's an evolution, but then eventually you find the whole thing. You could forget about how the time steps went. Learner, this is some classical complex analysis theory, actually, or tool. And well, stochastic, you kind of, that's the point of the lectures, that there's some probabilistic tool or point of view. So let's see. So I set my problem in some rather concrete way. And I should have already maybe drawn something in the bottom. Let me do that in here. Because I told you how I want to have this uniformization, which means that you can always send the domain to the disk. And then the points go somewhere. And then I can have the interfaces here, right? And okay, they do something. And now if I look at just one interface, like over there, it's easier because the question mark is not there. So let's see. So I could have my blob, which I send to disk. But what I actually want to do, I want to send it to the half plane because it's somehow easier for me. So now we're looking at one of these. I'm forgetting now the red and blue because it's insignificant for the model. I'm only interested in marked points, let's say X and Y or more. and this kind of interface, which I need to describe. So I could decide that they go to some given points, because now there's just two, like that. So here is maybe phi x. And I guess I kind of have some orientation. So now I'm exploring from x and ending at y. By planarity, I have to end in the other point, right? So then here is going like that. But now what I want to say that maybe the side. So now x is going to 0. And the other point goes to infinity. This is psi of phi. Okay, you can forget about the maps now. So what I'm trying to say is that I can just focus on my favorite geometry because of the conformal invariance somehow. So I'm supposing some conformal invariance should hold, not only scale invariance. So for mathematicians, this would be conjectural, right? From what I've said, but it's actually proven for Ising model. For example, a critical. Yeah. So can focus on half plane, and then
I'm sorry.
yeah.
For the, so you're saying that for the Ising model, it is known that the, so what are you saying when you were saying conjectural conformal invariance versus conformal invariance? I mean, I have this thing in the complex plane. I should be able to conformally do these maps.
Right.
But you're saying that something about the physics is known to be preserved in the Ising model, but you're not assuming this, and it's not proved for these other models?
Great question. So I go back here a little bit. So I was imagining this discrete model and those dots there. And then this interface is a lattice path. I'm just lazy to draw it like this exact thing. And of course, it cannot be exactly conformally invariant because it's discrete. But I believe that, it's arguably the case that at the critical temperature, we should have scale invariance in the scaling limit when the mesh goes away and the curve somehow survives. But then for a mathematician, to prove that the limit exists, for example, is extremely non-trivial. So this was one part of the Fields medal result, which is a little bit, I guess I'm not presenting it very well. So it's an amazing result, which maybe says that this is very, very delicate when you're actually a mathematician and you want to see like everything proven rigorously. So to prove this limit exists and to identify to something that has this conformal invariance, I'll tell you what conformal invariance means very soon. So this is a big theorem. And then you can say it's proven that we have this conformal invariance. And if we know that, here in this kind of domain with no holes, of course, I can send to some other favorite domain and study the model there. And if you like measure theory description, what is here is the Gibbs measure. I called it P Gibbs. So here is another measure, right? Which is some P in the disk. So this is in some D. Okay, so disk has two fold thing, right? It's a different D. So what the point is that this measure here is the same as I would transport from there. And I would call it the push forward. So something like that. Because in principle over here, I can put the Ising model here from the formula was erased already, which was this nearest neighbor interaction, blah, blah, blah. Or I could take whatever was here and move it by the map. But I don't know that they're the same, right? A priori. Maybe it's obvious to you that they are the same, but not to me. And this should somehow behave the same in the continuum. And actually, I think they are not the same unless you're in the critical, because outside of the critical temperature, you have some mass, which is some kind of typical scale. Let's say you scale the thing, that's the conformer. Somehow things are gonna change, and the mass is keeping track of the change, and the mass has to do with like how far you're from this, in a very heuristic way. Okay, so somehow it's not clear. That's why I wrote conjectural/proven. And there are many models that this is not proven yet. And I guess we don't really know how to do it, so we are a bit stuck. So we move to work on other things. But for this model, it's proven. Yeah.
Maybe we should stop soon.
Sure.
Over time.
Oh yeah. Happy to. Let me just make one note. So because of the conform invariance, if I believe it's true, it's sufficient to describe my model here and also the correlations here. So then next time, what we will do, so suffices to construct this, I call it the SLE curve of curves plus in half plane. So there might be more points than 2, of course, if there's more curves. But somehow this is what I'm then gonna do. And then in more other geometries, you need to figure out what to do. But yeah, sorry. Like I said, I don't keep track of time very well. But I'm happy to explain more in private also if there's something that's not clear from me. Thanks.
Maybe anybody has question maybe? Or we have question after?
We had some to read.
Maybe one quick question if someone wants, or otherwise we can ask after the talk.
I will be here the whole time. So.
Okay, so let's thank Eveliina again.
We go back to take our coffee break.
Coffee break?
Yes, coffee break.
No, it's not asking the same thing.